So good evening all. So today I will take a problem solving session 5 on the week 5 on the chapter liquid extractions. So here is a brief recaps. Introduction to liquid extraction, then liquid equilibria, then effect of temperature on in LLE, then design next stage design calculation of the single stage of extraction. I think all of you have gone through the week 5 lectures which are available on the SWAYAM portals. So based on these topics, I'm going to take up problems like MCQ and numericals. And meanwhile, I will explain the concept with respect to the questions. One minute, we are going to start this metric. Color blue. So question 1, which of the following is a primary objective of the liquid extraction? Like option given, generally liquid extraction is used to separate the solute from the one liquid phase into the another immiscible liquid phase with the help of the solvent. Like for example, aesthetic 1 minute, like 2,3-BD, BD and waters. Generally, it is present in the fermentation routes. So here's the 2,3-BD present like 10% and waters 90%. So like here is a water is a carriers and 2,3-BD is a solute, right? So general solute denoted by the C and carrier denoted by the A. And here's the solvent used like butanol, right, to separate the 2,3-BD from this feed. Like this is the feed, right? So here now come to the option 6. So to separate the solid's impurity from the liquid, to extract the solute from the solid matrix, no, to separate the solute from the one liquid phase into the another immiscible liquid phase. So option C is correct. Check also option D, to crystallize the solute from the solution. This is a this is crystallization. So this is not. So moving to the question number 2, which of the following is not an advantage of the liquid extraction over the distillations? So here is as the advantage of the liquid extraction over distillations. Means not advantage. So check, we have to check with the option wise. Like first A is the ability to separate the heat sensitive components. So in this question asks the not advantage of the LLE over the distillations. So it can separated by the also LLE, lower energy consumption. Yes, here as compared to the distillation, it uh, for a distillation it has a low energy consumption, and see the better separation of the component with the close boiling point. Yeah, it is possible either in a liquid extraction. D, the simpler equipment requirements. So this is a not advantage of the liquid extraction, because for a single cell it is mm, for a no, liquid extraction there are the various steps. So for the single step is the simple, but for the if you go to the for the multiples, so needs a the means complex equipment requirement in ELLE. So option D is a not advantage of the liquid extraction over the distillation. So option D is correct. Moving to the question number 3, in a ternary system consisting of water, acetone, and chloroform, what is the role of the acetones? So here the carrier, this is a solute, and this is a solvent. Because there is also criteria for the selection of the solvent for the to extract the solute from the feed. So here is the acetone is a solute in these ternary systems. Moving to the question number 4, which of the following is best describe a tie line in a liquid phase diagrams? Here is a phase diagrams like yes, see, right? Yes, right. Here is a 100% C, 100% A, and 100% B, right? So this side denote the percent of the C. This denote the percentage of the B. This denote the percentage of the A, right? Right. This is the binodal curve. So here is a tie line. So here is like B. Right. So this indicates the rapidness phase, the composition in the rapidity phase, and right side show indicates composition in an extract phase. So here, so here tie line indicates the equilibrium between the two immiscible phase. Right. At equilibrium conditions, like here is a means extract and rapid. Like for example, here is a two mixtures, one like feed and solvent. So after mixing, so after getting means after attain the equilibriums, so we analyzes the samples in the both phases. So that's the compositions, means after the attain the equilibriums in a two immiscible phase. Here means after from the two phase like extract phase and rapid phase. So option for this answer, the answer is a line indicating equilibrium between the two immiscible phases, right? So here is in the B option, the mention that a line connecting the rapid and extract phase. Yes, but here is a missing the one terms that is a equilibrium, right? So this is not a line connect 2 points of a different components. No, this is not also a line that indicates the overall composition of mixture. No, right? So here a particular line here is a P is a plate points, right? So here means is a here attend the like single means single page. Right, so at that point, so it cannot separate the solute from the feed. In separation it cannot possible, so at this point. Into the question number 5, in a liquid equilibrium studies, a system called a type 2 IP. So like here is the solute, carrier, and solvent. Solvent, right, denoted by the B, A, and C, right? If like for a type 1, A to C and A to C and C to B are miscible, and A to B are partially miscibles. A to B partial is a partial miscible. Right. These are for type 1 systems. In type 2, so B and C and AB are a partially miscibles. Right. Is to A to C are miscible in all proportions. So option is correct. So BC and AB pairs are a partial miscible in a type 2 systems. Question 6: how does an increase of temperature generally affect the solubility of solute in the liquid extraction process? So generally, when we increase the temperature of the any system, so it increase the solubility, right? Like A plus B, here systems A plus B mix in way in heatings, so it's the increase the like solubility, like is so we trying to mix the A into the B, so it increase the solubility of A into the B. But here is in the liquid extraction there are three components. So in this case, it increase the solubility in one phase, that is like extract phase, while decreasing it in others. Means like solubility of the solute increase in the extract phase, means in a solvent phase, then raffinate phase. Raffinate means rich in waters. Option C is correct. Now, question 7: which of the following statement is true regarding the effect of temperature on the liquid phase separations? So here is the option given: higher the temperature, always increase the phase separations, right? Uh, uh, high, because this is not possible for the all the systems. Higher the temperature may lead to the single phase region, so it can possible. Sorry, 1 minute. C1B, right? Lower the temperature, always the decrease the phase separations. And temperature does not affect the liquid equilibrium. This is not. Lower temperature always the decrease the phase separations. So option B is correct here. because at a higher temperature it may lead to the in a single phase regions. Question 8: how does the temperature influence the distributions coefficient in a liquid extraction? So it decreases the distribution coefficient. No, it has no effect of the distribution coefficient. So it increases the distribution coefficient. The effect depend on the nature of the solvent. Okay, it's a effect depend on the nature of the solute and solvents. Yes, it affects, but it depend on the nature of the solute and the solvent. Percentage is correct. Move to the question number 9. Which of the following changes cause a type 2 liquid system to become a type 1 systems? So it change by increasing the temperatures. Like here, 1 minute. AC, BC, and AB, right? So these are the partial miscible. These are the miscibles in a type system. When increasing temperatures, AP. So BC2 changed. So in a miscibles in all proportions like AC and BC by increasing temperatures. So it's a become a type 1 systems by increasing the temperatures. Question number 10. Consider the distribution of the solute C in a two partially miscible solvent A carriers and solvent B. What is the selectivity of the separation at the plate point? So at plate point, the selectivity is a 1, right? The selectivity denoted by the B. So it is a distribution coefficient of solute divided by distribution coefficient of carrier. So at a plate point, so the separation is a 1. So there is a no possibility to say separation. So for separation, so the selectivity should be greater than 1. So we can say that it's possible to separate the solute from the feed. What should be generally to be minimum fractional density difference between the carrier and the solvent, so that phase separation may not be very difficult. 11. So it should be generally the density, the difference between the carrier and solvent should be 5% for easy separations. Question Question number 12. In a single stage liquid extraction, what is the key variable for determine the amount of solute extracted? So agitation speed, pressures of the systems, temperature of the system, volume of the systems. So here is the key variable. So if you increase the solvent, so there will be the more extraction efficiency of the solute. So option is A. Because the temperature of systems, it increase the solubility means it's more solute can transfer it into the solvent beds. But if I increase the solvents as compared to the temperatures effect, so it impact more of a volume of the solvent. Means higher the selectivity of the mother of particular solvent, so it means required the less solvent. If I less than one, so it would require the more solvent to separate separate the solute from the feed. Moving to the question number 13, for a single stage extraction, which equation is typically used to calculate the distribution coefficient? So distribution coefficient is a amount of solute extracted into the extract phase divided by amount of solute in the raffinate phase, right? So we can say that like xc sorry yc divided by x c. So it is a mole fraction of solute in the extract phase, means that's in solvent rich phase. Here xc denote by the mole fraction or mass fraction of solute in the raffinate phase, which reach a water means rich water phase. Check the options. So solute in a extract phase divided by solute in a raffinate phase. Option B is. Coming to the question number 14, which of the following is an important consideration when designing a single stage extraction? So check the option. Just check the partition coefficient of the solute. So option B is a correct. Question number 14, right? Moving to the question number. In a single stage extraction, if the solvent to feed ratio increase, solvent like denote B to feed, you can say yes. If increase the amount of solute extracted, so should be the increase, because here we increase the solvent, right? So there will be the more extract of the solute from the feed, should be increased. 15. Right. Question number 16, which factor is not typically considered when design a liquid extraction process? So in design the LLE extraction process, we consider the immiscibility of the phases, distribution coefficient, viscosity of the solvent. So it's option D is the thermal conductivity of the solvent. So it's not the consider factor for the selecting the solvent or by designing the liquid extraction process. So option D is moving to the question number 17. Which of the following is a critical factor in choosing a solvent for a liquid extractions? Check option. Now you have to select the high solubility for the solute and low solubility for the other components. So this is possible. The high solubility for the all component, not possible. So complete miscibility with the feed liquid. So it cannot possible for the separation. High boiling point and viscosity, no. So for For a selection of the solvents, the solvent should be the low viscosity and also low boiling points. So option A is a correct. Because at a higher boiling point, it requires a lot of energy to uh, convert. Because suppose in a rapid phase, generally rapid phase is a water rich phase. Suppose uh, okay, so option A is correct. Question number 18. What is the purpose of using a co-solvent in a liquid-liquid extractions? So here to increase the volatility, absolute no. To improve the distribution coefficient of the solute. Option B is correct. Moving to the question number 9. So this is a numericals. The here statement 100 kilogram of the 50% of the solution of the C in a carrier is equilibrated with a 70 kg of the solvent B containing 2% of the C. So at equilibrium, the rapid phase has a mass of 80 kg and has a 52% of A and 8% of B in it. What is the selectivity or separation factor of the C? So in these questions, so we have to calculate the separation factors. So here denoted by C, generally C denoted by the beta, right? So I have to calculate. So in this first have to know what factors means, what are the properties given. So here feed is given 100 kg, right? And there the fractions, weight fraction like xc in a, yep, right, means mole, you can say mole fraction also. Mm. Mole fraction of the solute in a feed 0.5 and xa means carrier, it's a 0.5 in a feed, right? And solvent, yes, is a, so I directly written here with the help of flowchart. Feed solvent, right? Yes, solvent. Mhm. Mhm. Denoted V extract rapid, right? So XCF given solvent quantity given 70 kg, right? X sorry, Y C in solvent 0.02 given. So y b in the solvent 0.98, right? 1 minus this, so we'll get the this mole fraction of the solvent in a solvent stream. So here E did not given, so we have to calculate, right? And also others means all the composition we have to calculate in terms of the mole fractions. And R given 80 kg, and mole fraction XA are given here 0.52, and B XB, right, in a rapidness stream 0.08, 0.08. So you will get XC R 1 minus this plus this, so you'll get 0.42, right? And this separation factor calculate using these relations, like distribution coefficient of the solute divided by distribution coefficient of the carriers. So YC XC, so YA divided by XA, right? So this is the distribution coefficient of solute divided by distribution coefficient of the carrier, right? So we can make this expressions like YC divided by YA, it extract, right? XC by XAR, right? So we know the XCR, XAR, YC above in extract the composition in the extract phase we have to calculate. Okay. So first do the material balance, overall material balance, OMB to F plus ES, right? So it's equal to E plus R, right? So F plus F given 100 plus solvent quantity given 70 kg plus E, how to calculate E, R given 80, right? So E is a 90 kg, right? So now how to balance on the solute balance, right? So F XCF plus B Y C B plus E to mole fraction of the solute in the extract phase plus R quantity of raffinates into mole fraction of the solute in the raffinate streams, right? So here we don't know this quantity only, so all the givens, so put all the value here, so you will get the Y C mole fraction of solute in the extract phase, so it's a 0.21. Now take a means component balance on the carrier balance, right? Yep. Mole fraction of the carrier in a feed plus quantity of the solvent into mole fraction of the carrier in a solvent streams equal to quantity of extract phase into mole fraction of carrier in a extract phase plus R mole fraction of the A in a rapid phase, right? So here we have to calculate this quantity only. So all the given and some here either you calculated. So here the y is a 0. So all the given. So y a e is equal to 0.093. So now put in that relations b is equal to 0.21. Here y is calculated and y also calculated 0.21 divided by 0.093 divided by 0.4 means xc in the rapid phase given and xa also. So it's a 3. So it's the separation factor is greater than what, so it's the possible separation of this solute from the feed. Question number 19, 100 calculated already. The following mass and solute concentration are given for ideal single stage extraction systems. If is equal to 500 kg, mole fraction of the solute in the feed 0.4, then yes, solvent quantity 400 kg, and mole fraction of the solute in solvent streams is a 0. So it's among pure solvents. The amount and concentration of the extract are E is equal to 550 kg, Y is equal to 0.33. So what is the distribution coefficient K of the solute at this condition of the mixtures? So to calculate the distribution, K is equal to YC mole fraction of the solute in the extract phase divided by mole fraction of sol X mole fraction of the solute in a rapid phase, right? First, do the overall material balance OMB, right? So F plus S equal to E plus R, right? So here is a given the YE mole fraction of the E in the extract phase, right? So here YC given, so we have to calculate the XC in a rapid phase. Calculate the distribution coefficient of the solute. So F is equal to 500 plus solvent 400 is a 550 and R. So you'll get R 350. Now take a solute balance. F X F B X S E. So here I the mole fraction of the solute denoted as given in the question statements. So otherwise you can take like y xc in a feed, like xc in a feed. Right. So 100 into 0.4 plus b 400 0 e 550 into 0.33 r is a 350 into x r, right? So x r can say x c r, so 0.05285. So put this value in this equation. So k is a 6.24. Moving to the question number 21, a mixture of 100 kg of feed solution contain a 40% by weight acetic acid and 60% 60 waters. The solution to be treated with a 150 kg of pure ethers to extract the acetic acid. At equilibrium, the distribution coefficient Kd 2.4. So C ethers and C waters. C ethers and C are the concentrations. 1 minute. Is the extra part. So determine the amount of acetic acid in the ether phase after the equilibrium is reached. And second question, calculate the amount of acetic acid remaining in the water phase. So in this question given the Kd, so Kd is a amount of acetic acid in a ether phase divided by amount of acetic acid in a raffinate phase. So like here so like we later consider x be the mass of acetic acid in the extract phase, means ether phase, right? So you can write down x, right? So initially is the 40 weight percent, means 40 kg of the solute. So 40 minus x, right? That's the quantity of acetic acid in the rapid phase. So Kd value given is a 2.5, right? To calculate the x, so like 28.57 kg. That's the answer of the first question. And second, calculate the amount of acetic acid remaining in the water phase. To calculate this, just like this distance 40 minus this x, 28.57. This is the 11.43 kg. The answer of the second question. So moving to the question number 22, 1000 kilograms, 100 kg of an aqueous solution containing 50% acetone is contacted with a 800 kg of chlorobenzene containing 0. mass percent acetone in the mixture settler unit, followed by the separation of the extract and raffinate phase. To determine the composition of the extract phase and raffinate phase and a fraction of acetone extracted, means extraction efficiency of the acetones from the mixture from the feed. Also calculate the amount right of a solvent required if 90% of acetone is to be removed. The equilibrium and tile line data are given below. So here is the data given, like after attaining the equilibriums. So first we write down the given quantity. Ap is equal to 100 kg, right? This is a 800 kg, and mole fraction of solute in the feed 0.5. Mole fraction of the A in the feed is a 0.5, right? So here in this feed, so mole fraction of the solvent is a 0, right? So xb in the feed is equal to 0, right? In a solvent stream, so given 0.5%, 0.5 mass percent. So y c in a solvent stream is a 0.005. So you'll get the YB. So 1 minus this. So it's a 0.995, right? Like overall material balance, like A plus S equal to M after mixing equal to R plus E, right? So A plus S is equal to M is equal to 1000. Okay, 1000. Sorry, yeah, 1000. So 1800 kg of mixtures, right? Now we have to calculate the composition at a mixing. So to calculate the this ones, xmc equal to fcf plus solvent yc, right, divided by m. So you put in this equations all the value, you get the 0.28. So it's a molar means composition at a after mixing, after two means solvent and feed. Now the equilibrium that are plotted using the right triangular coordinates here. 1 minute. Here. Based on the XC means acetone in a raffinate phase and the extract phase. So yes. So So first the means whatever the data given, so so draw this rectangular coordinate and xy diagrams, right? So like here if is a uh, it means 0.5, right? Means solute concentration 0.5 is a solvent, right? So now if you draw the lines, so xm means composition at mixing, so it's a 0.28, like here 0.2, so we'll get the like 0. Here, so we don't know the composition at extract phase and rapid phase of the solutes. So now with the help of you draw the some like xy diagrams with the help of the given the data like xc acetones and as yc in a extract phase. Now so draw the here is 0.28. Draw the straight lines. So then draw the lines. So this is the equilibrium lines. The draw the line. So that's the rapid phase, and the upper curves. So you get the means more quantity or mole fractions composition of the extract phase. So it's R value is 0.23. 6 and E is a 0.302, right? So as E plus R equal to 800, right, kg. So sorry, 1800 kg, right? Now to E by R is a xm minus xr ye minus xm, right? So put the value here. Xm is a 0.28, xr is a 0.236, y is a 0.302, and xm is a 0.28. So based on this equation, like this, consider equation 1 and equation 2. So based on that, so you will get the value of E is a 1200 kg and R is a 600 kg, right? Now mass of acetone in a feed is a 1000 into 0.5, so 500 kg, right? Now acetone entering with a solvent, acetone entering in a solvent, right? 800 into 0.005, so 4 kg, right? So net amount of acetone transferred to be the extract film is equal to 362.4. Okay. First we need to calculate. So mass of acetone in the extract phase. First to calculate the mass of in a extract phase, right? So E into YC E, right? So 12 the quantity of extract phase is 1200 kg, 1200 kg into YC mole fraction of the solute in the extract phase 0.30, right? 0.302. So 362.4 kg. Now come back to the here. So net amount of acetone transfer to the extract the stream. So 362.4 minus 4 is equal to 358.4 kg. Now we have to calculate first fraction of the acetone removed by the extractions, right? So is 35.84 kg in a extract phase divided by initially in a feed present the solute 500 kg, right? Into 100. So 71.7%. So this is the extraction efficiency of the solute using this solvent like chlorobenzenes. Now moving to the second part, calculate the amount of solvent required if a 90% of the acetone is to be removed, right? Second part. 90% of acetone is removed. So acetone remaining in the aqueous phase AP is a 500 into 0.1, right? So that's a 50 kg. Because initially feed present in the initially solute present in the feed is a 50% acetone, means a 500 kg. So if in this second statement given the means 90% acetone is removed, so means here 0.9 portion in the extract phase, so 0.1% means 10% in a raffinate phase. So it's a 50 kg, right? So now it is noted to be noted that at this low concentration of the solute, the mutual solubility of water and chlorobenzenes is negligible. So therefore, the raffinate may be assumed to be the virtual free from the chlorobenzenes. So in this raffinate, the chlorobenzene no present the chlorobenzenes. So now the concentration of acetone, concentration of acetone in the raffinate phase, in the aqueous phase, you can say also aqueous phase. So 50, right? Here is a 50 divided by total quantity of the raffinate. So 550, right? So 0.0909, right? So at the XCR 0.9, so we'll get a YC mole fractions of C in a E in the extract phase from the equilibrium curves 0.105, right? Zero point 0 here, like 0.09 till like here is 0.1. So draw line, right? All right. Like above, so that's a 0. 105, right? Now R is a 550, right? Now, if S is the mass of the solvent required, then we can the material balance for the solute. Material balance for the solute balance. So 1000 to 0.5 plus S to 0.005 equal to X plus 450, right? Into mole fraction of the solute in the extract bed 0.105, right? Plus 550, right? 550 into 0.0909, right? This is equal to 450. Okay. So here is the means rapid phase like 550. So 1000 minus 100, 1000 minus 550. So it's a 450. 450 like solute. So all this, so we'll get the is the 4027 kg of chlorobenzene required for 90% acetones, right? So here using this 800 kg, so around the 71 71%, 4027, right? So for the 90% extraction efficiency, so for 4027 to 4027 kg solvent required. So I cover all the question based on the these topics. So I conclude the today's sessions. I will meet. So we will meet on the next Friday on same chapters on a different topics like LLE designs for the multi-stage. Design calculation for the multi-stage extractions. So okay, thank you.